Welcome to this course on heavy metal pollution from mining activities. My name's Luke Bridgestock. Some background about myself. I obtained my master's degree in geology and PhD in isotope geochemistry from Imperial College London. I then worked as a postdoctoral research associate for about 5 years at the University of Oxford, and since then have been a Leverhulme Research Fellow at the University of Cambridge. My research interests are in the cycling of metals in the environment. And I'm interested in this research topic for a variety of reasons, including those the subject of this course, which are the perturbation of metal cycles due to human activities and the consequences of these perturbations on the health of ecosystems and human populations. This course is split into 3 parts. In the first part, we're going to learn about how people are exposed to heavy metals and how to assess the toxicity risks of heavy metal exposure in various populations. In the second part, we'll learn about how mining-related processes can release heavy metals to the environment. And in the third part, we'll learn about different remediation techniques for acid mine drainage, which is a particularly important process in mining operations that releases metals to the environment. So in each of these parts will involve a short lecture of about 30 minutes, followed by a practical session where your skills and knowledge you've learnt into practice. And so this is the start of the lecture of the first part of this activity, focusing on the toxicity risks due to local populations caused by heavy metal exposure. Exposure to heavy metals can result in harmful effects for both wildlife and humans. To be able to protect different populations of human from the toxic effects of heavy metal exposure, we first need to understand 2 things. We need to understand how people are exposed to these metals in their daily lives, so the exposure route. And this, for example, could be due to eating certain foods or from the water that they drink. Secondly, we also need to understand the sources of these metals to the environment and their transport pathways to the point of human exposure. If we can understand these 2 things, then we can start to develop strategies to protect human populations from dangerous levels of metal exposure. Human activities, and in particular mining, have been a major source of heavy metals to the environment during recent history, and this has of course greatly elevated the risks of different populations from developing metal toxicity problems. So by the end of the first part of this course, hopefully you will all have learnt these 3 important points on this slide. Firstly, hopefully you'll all have learnt what are heavy metals and why they are important water quality parameters, what the routes are by which people can be exposed to heavy metals, and finally you would have learnt about how to assess toxicity risks due to chronic metal exposure in different populations of people. So, what are heavy metals? This is a term used throughout the literature in environmental science, but it's very poorly defined. It generally refers to metal elements with a high density or atomic number, but different studies often use this term to refer to different groups of these elements on the periodic table. Trace element and trace metal are other commonly used terms in replace for heavy metals. It's worth noting that the elements arsenic and selenium are technically non-metals, but they show similar chemical behavior to metal elements and are often referred to as metalloids. And these can often cause toxicity problems in human and wildlife populations. and so they are often included in studies of heavy metal pollution. So why are heavy metals important? Well, many heavy metals are in fact important nutrients that are essential to life, and these include, for example, iron, zinc, and copper. And we need at least some of these elements in our diets to remain healthy. However, exposure to high amounts of all of these elements, and in particular these elements in certain chemical forms, result in toxic effects for life. And so both the nutrient and toxic roles played by these different metals, in particular those I've highlighted in red, make them a key water quality parameter to be measured routinely in environmental studies. So it's important to note that while human activities, including mining, have released large amounts of these metals to the environment, high concentrations of these elements in water sources and food and other natural components of the environment can occur purely due to natural processes. And it's a common misconception that the presence of heavy metals in different parts of the environment are purely due to anthropogenic perturbation. And so a key challenge in studying issues of heavy metal pollution are distinguishing between naturally occurring levels of metals in the environment versus those released by human activities. And so a particularly important example of where natural processes can result in high concentrations of elements that can cause harmful issues for public health are concentrations of arsenic in groundwater. And these can be well above the levels deemed safe for drinking water, purely due to the natural dissolution of mineral phases in aquifers. And this is a major concern for public health in the delta regions of large Southeast Asian rivers, including the Irrawaddy in Myanmar. This is not an issue covered here, but this is something that's considered in other courses as part of the TIDE program. So another common misconception is that all heavy metals are toxic to life, and that we need to reduce our exposure to these heavy metals as much as possible to be healthy. Of course, this is not true. As I've just mentioned, many of these elements classified of heavy metal in fact are key nutrients, and not having enough of them in our diet will result in us having health problems due to being deficient in these elements. And examples of this include intakes of selenium, zinc, and iron, for example. There are certain heavy metals, however, that have no known nutritional value, and notable among these are mercury, lead, and arsenic. And in this case, it is in fact desirable to have the lowest possible exposure to these particular elements as possible. And so, in detail, the nutritional value versus the potential toxicity effect of intake of an element will depend on both the amount that a person has in their diets and is exposed to in their daily lives, as well as the chemical form in which that element occurs. So this is the speciation of the element. So how are people exposed to metals? This can occur through different routes, mainly inhalation, so breathing particles, tiny particles containing metals into the lungs, and these metals can then dissolve and be transferred into the blood. The second pathway which people can be exposed to metals is through ingestion, and so metals in the water that people drink and in the food that people eat. And finally, through dermal exposure, which is the absorption of metals and different chemicals directly through skin to the blood. And so inhalation and dermal exposure are generally only important for specific professions and very specific circumstances where people are working with hazardous chemicals. And in part 2, we'll discuss an example of this related to the use of mercury in artisanal gold mining operations, a particular issue for Myanmar. However, generally speaking, the majority of people, ingestion is the most important exposure route for uptake of metals into their bodies. And so that's the exposure route that we're really going to focus on in more detail. So if exposed to high amounts of a metal element, people will experience adverse health effects due to metal toxicity. And this is because these metals can disrupt important biological processes occurring in our cells. Many metal species can also cause cancer, but the non-cancer toxicity effects due to metal exposure can be split into 2 categories. So acute toxicity, and this refers to harmful effects on health due to short-term exposure to a large amount of a toxic substance. And the symptoms of metal toxicity following this short-term exposure are going to be quite quickly apparent. However, most cases of metal toxicity are more subtle and involve the exposure to lower amounts of heavy metals over long time periods, many decades often. This is known as chronic toxicity, and the symptoms of metal toxicity develop more slowly, often over the lifetime of an individual. In this case, it's often hard to diagnose metal toxicity as the cause of the resulting health problems, and so that many people can develop chronic toxicity due to metal exposure without realizing it. And in fact, identifying groups of people that are at risk of developing chronic metal toxicity over their lifetimes represents an important first step to be able to address these issues. And in the latter part of this lecture, and in particular in the practical session of this part of the course, we will focus on learning about how we can do this. Okay, so we're going to just pause the lecture here for a few minutes, and I want you to think about these 3 statements, and based on what you've learned so far, try to decide whether or not these statements are true or false. So if you just take your time, pause the lecture, and read through and think these statements before continuing. So hopefully you all got that statements 1 and 2 were of course true. So certain heavy metals are important nutrients, but exposure to too much of any heavy metal can often result in harmful toxicity effects. So question 2, inhalation, ingestion and dermal are all exposure routes, all important exposure routes for heavy metals. But statement 3, so to remain healthy, we need to try to minimize exposure to all metals and metalloids is false. So of course, some of these elements, as we've noted, are in fact key nutrients, and we need at least certain doses of them in our daily diets to remain healthy, with examples being selenium and iron. So we identified ingestion as being the main exposure route for metal intake for the majority of people, and this can be either through water that we drink or through the food that we eat. And so to try to protect populations from excessive metal exposure via drinking water, various government organizations and health bodies have set legal limits, or at least guideline limits, concentrations of different elements in water that are deemed safe for drinking. And here are the levels set for many of these toxic elements by the World Health Organization for your reference. So these represent environmental standards which can be used to compare our measurements of data against to assess whether or not there's a risk that people with access to this drinking water will develop chronic toxicity problems over time. Worth noting that many of these levels have been continually set to lower and lower values over the past few decades as the harmful effects of long-term exposure to these elements become more apparent. So, for example, in the UK, we recently lowered the legal limit of lead in drinking water from 25 micrograms per litre to 10 micrograms per litre for this reason. However, it's actually the ingestion of food that is the most important exposure route for most heavy metals and most people. And so we're going to consider how heavy metals from various environmental sources can end up in our food supplies. This can occur either through the uptake of metals from water used to irrigate crops into the soils and eventually into plants, and as well as into fish and seafood, which can accumulate large amounts of certain metals from the water in which they grow in. A particularly prominent example of metals which can be accumulate in crops that we grow include cadmium as well as arsenic, which can accumulate to very high levels in rice. And eating rice can therefore be an important vector for metal exposure of these metals to many people around the world. A prominent example of a large case of cadmium poisoning via this route occurred in Japan in the early 20th century and really shone a spotlight on the harmful impact of this element. And so mining operations upstream from this region in Japan contaminated the rivers with cadmium. And this cadmium then accumulated in the soils downstream, which was used to grow rice. The rice accumulated large amounts of this cadmium, and so all the people in this area became quite ill from eating this rice. Metal exposure via eating food is such a dominant exposure route because organisms can accumulate metals in their cells to much higher concentrations than those found in the surrounding environment, and this is known as bioaccumulation. This occurs because organisms uptake metals dissolved in the water or the environment that they're living in faster than they excrete them from their cells as waste. And so over time, the longer these organisms live, they accumulate metals to higher and higher concentrations in their tissues and cells. Mercury is a very toxic heavy metal that's particularly prone to bioaccumulation in aquatic ecosystems. So photosynthesizing algae, so living at the bottom of the aquatic food web, can feature mercury concentrations between 2 or 3 times higher than the waters they live in due to this process. So bioaccumulation of heavy metals will continue up the food chain. For example, zooplankton that live off these photosynthesizing algae will eat a large amount of this algae over their entire lifetime, and they will accumulate a large fraction of all of the mercury in this algae and hold it in their cells. And so this increases the mercury concentration in the zooplankton to an even higher level than that in the algae. And so this process can be repeated in many steps of the food chain, meaning that fish living at the top of an aquatic food chain can have mercury concentrations in their tissues up to 1 million times higher than the waters that they live in. And collectively, this sequence of bioaccumulation steps up the food chain is known as biomagnification. People who eat this fish can then be exposed to huge amounts of mercury. And because of this, the consumption of fish and shellfish is a really important exposure route for mercury to people, as well as many other toxic heavy metals that can biomagnify in this way, for example, cadmium. Concentrations of mercury and these other metals like cadmium in the water bodies which these fish live in are typically much lower than the safe drinking water guideline values set by the World Health Organization, for example. So even in areas that have been impacted by metal pollution, concentrations of mercury dissolved in water are typically very low due to this metal being particularly insoluble, and represent very little toxicity risk due to exposure via drinking water. Fish or shellfish living in these waters, however, can, as I mentioned, accumulate huge amounts of mercury and other metals. And eating these animals will be the dominant exposure route to these toxic metals to the wider population. Due to metal accumulation by these animals, the measurement of metal in their tissue can also often be a more useful way of assessing levels of contamination from these pollution sources rather than direct measurements of the water themselves. So I want you to pause the lecture again whilst you think about these three statements and decide based on what you've learnt in this section of the lecture whether they're true or false. So statement one, hopefully you recognise this is true. Different government bodies and organisations have set limits for maximum safe concentrations of metals in drinking water, and these represent environmental standards, reference values that can be really useful when conducting environmental studies. Statement two is false. So it's not only is it important to consider heavy metal concentrations in water when you're assessing toxicity risks to populations, you need to consider the food, and in fact the food is often the dominant vector of metal exposure to most people. And statement three is true, so biomagnification is a process by which certain metals increase in concentration in living organisms as you go up the food chain. To protect populations from being exposed to dangerous levels of heavy metals, it's important to be able to evaluate the risk posed by chronic metal exposure by different exposure routes and activities, for example, drinking water or eating fish. To do this, the estimated daily intake of a metal in micrograms per day per kilogram of body mass is compared to a level that's considered safe using a hazard quotient. If the hazard quotient is higher than 1, then it means that someone's metal intake every day is exceeding this level we consider to be safe, and that these people are at risk over a long time period of developing chronic toxicity problems. If the hazard quotient is less than 1, then it means that this metal intake is below what we think is the safe level, and there's minimal risk of these people developing chronic toxicity problems. These recommended daily intake values, the safe levels, are typically evaluated using experiments on animals. And here in this table are shown some of these reference values that are commonly used by the US Environmental Protection Agency for conducting environmental impact assessments. The average daily intake of metals by a group of people by ingestion, so either by eating food or drinking water, can be estimated using this equation shown here, developed by the US Environmental Protection Agency. Similar equations, slightly modified in form, can be used to assess average daily intake of metals via inhalation and dermal absorption exposure routes. And so in the practical, we're going to learn how to use this equation in detail to assess chronic toxicity risks from a variety of metals via different exposure activities in a hypothetical case study. And importantly, you will also start to critically think about these different variables in this equation and how you might approach choosing suitable values for these variables when assessing these types of risks for different groups of people. So this brings us to the end of this first lecture as part of this course, and we're going to just summarize the three key learning objectives set out at the start of this lecture, which hopefully you will now all understand. So the first one was to understand what are heavy metals and why they're important water quality parameters. And we should all now know that there are a group of metal elements on the periodic table which are particularly poorly defined, but they're important water quality parameters because some of these elements are key nutrients that life needs to thrive, whilst pretty much all of these elements will become toxic and have negative impacts on the health of organisms at high enough concentrations. The second key learning objective was to understand what the important routes are by which people can be exposed to heavy metals. And we identified inhalation, so breathing metal-rich particles into the lungs, ingestion, so metals which are either in the food that we eat or the water that we drink, and through dermal exposure, which is the absorption of metals through the skin from various chemicals. And we identified that ingestion is typically the main exposure route for the general population, and that in fact eating food is typically the most important exposure route for most people and most metals. So finally, we wanted to learn about how we can assess toxicity risks of chronic metal exposure. And we learned that we can do this by comparing the average daily intake of a metal of a particular group of people, averaged over a period of time, to recommended safe intake rates known as a metric called a hazard quotient. So now you're going to put the knowledge that you've learnt in this lecture into practice in a practical session, so the first practical session of this three-part course. So in this practical, you're going to assess chronic toxicity risks to people living in a hypothetical town due to exposure to a variety of metals via different routes. This town is next to a river, and upstream of the river there are various mining processes, operations, including a lead-zinc mine, and an area where river sediments are mined for gold by artisanal miners. And in part 2 of this course, we will focus on assessing the impact of these mining activities on releasing metals to the river. But for now, we're going to focus on the potential chronic toxicity risks to people in this town due to metal exposure. The people living in this town use the river as a source of drinking water. They also use this river water to irrigate their rice fields, and they eat fish that have been caught in the river. So the important question you're going to answer is, are these people at risk from developing chronic toxicity metal problems via these three different activities? So drinking water, eating rice that they grow in these, and eating fish from the river. To do this, you're going to calculate hazard quotients for these different metals and these different activities. So drinking water, eating rice, and eating fish. So just as a reminder, the hazard quotient is the ratio of the average daily intake of metal by a group of people to the recommended daily intake of this metal, which is considered to be safe. And this is in micrograms of metal per day per body mass of person. And so if this ratio is higher than 1, then it means that people's metal intake is exceeding the safe level, and there is a risk that they will develop health issues due to chronic metal toxicity. And the greater this value, so the higher this number, then this means the higher the risk. The recommended daily intake values for these different metals, or the safe level of metal exposure, are listed in the handout as reference values. However, to calculate the hazard quotients, you must first calculate the average daily intake for these different metals via these different exposure activities, being drinking water, eating rice, and eating fish. And you do this using the equation listed on this slide. And so this equation features 6 variables that must be set by the scientist conducting the risk assessment, and we'll talk now in more detail about what these variables represent. So C stands for the metal concentration in either the drinking water or the food being considered in this calculation, in micrograms per litre in the case of water, or micrograms per kilogram in the case of food. And this variable is set by the collection of samples of this material and the measurement of metal concentrations in a lab. The 5 remaining variables, however, must be set according to knowledge of the population of people being considered in the risk assessment. IR stands for the ingestion rate, which is the amount of water or food that is consumed by this group of people per day. And the ingestion rate is likely to vary between different groups of people depending on their lifestyle, and so it's desirable to obtain local knowledge to set this variable. For example, people living in different areas may eat different amounts of rice and fish in their daily diets. BW stands for the average body weight of this group of people being considered in this risk assessment. And again, this may vary between different populations of people, but generally speaking, you can assume an average of perhaps 70 kilograms for adults would be suitable. So these 3 remaining variables, EF, ED, and AT, stand for exposure frequency, exposure duration, and averaging time. So exposure frequency is the number of days per year in which the exposure activity occurs. So for example, in the case of drinking water, people are likely to do this every day of the year, and so you would set this value to 365. However, for eating certain foods such as fish, this may be less frequently done within different groups of people. For example, people in this population may have the habit of eating fish just once a week, in which case you would set this value for fish to just 52 days per year. Exposure duration and averaging time reflect the total length of time, either in years for exposure duration or days in the case of averaging time, for which the risk assessment is being conducted. And this is often set to the average lifespan of the people being considered in this risk assessment. And this long time scale over which this ADI is average reflects the fact that we're calculating chronic metal toxicity risks, so the risk of developing health problems due to this long-term exposure of these metals. And these 2 values reflect this long time scale over which we want to conduct this risk assessment. So your task is to use this equation to calculate average daily intakes, so ADIs, for 3 different metals: lead, cadmium, and mercury, for drinking water in this population of people living in this hypothetical town in question 1, and then repeat this same calculation for the exposure activities of eating rice in question 2 and eating fish in question 3. So for each of these exposure activities, the concentrations of these metals, so this C value, is listed in these tables. And I've also listed appropriate values that I think would fit for these other variables in this ADI equation that we've discussed. Once you've worked through these calculations, I then want you to think about these 3 summary questions, which will try to get you to think critically about how these calculations are conducted and how you might choose appropriate values for these different variables that we've discussed. And so I'd ask you to pause this lecture here until you've worked through these questions, these calculations, and had a thought about these answers to these 3 summary questions before moving on to reveal the answers. So here in red are the answers to these calculations, to these 3 questions for calculating the average daily intake and the hazard quotients for drinking water, eating rice, and eating fish for these 3 metals. And hopefully you've all been able to replicate these numbers. And so in the last part of this section of the course, we're going to discuss these 3 questions, which I hope you've all had a good think about. So the first question is based on the results of the hazard quotients. Which of the metals, so lead, cadmium, and mercury, and which of the exposure activities, being drinking water, eating rice, and eating fish, represent a chronic toxicity risk? So which of the hazard quotients are greater than 1? This should be pretty straightforward to answer. Hopefully you recognize that lead in drinking water has the highest hazard quotient of 3.1. This is followed by cadmium in the rice that people eat of 1.4. And finally, mercury in fish has a hazard quotient slightly higher than 1 of 1.3. And the remaining hazard quotients you've calculated are all below or well below 1, suggesting that these metals via these exposure activities represent minimal risk of chronic metal toxicity. So out of these 3 metals and 3 exposure activities that we've identified as presenting potential risk, lead in drinking water has the highest hazard quotient, and so this is the highest risk metal and exposure route for causing chronic metal toxicity in this population of people. And so just to note that hazard quotients can be used as a useful tool for ranking the relative risks of different metals and different exposure routes within population. And this can in turn be useful for prioritizing which of these issues to tackle when given a limited number of resources. So question 2 is to discuss how the variables in these hazard quotients and the hazard quotients you calculate would differ if you did this for children. And so as I hint in this question, children have a less body weight, and so this variable would be set to a lower value for children, and in turn this would increase the hazard quotient and the toxicity risk that would be calculated. However, hopefully you've also thought about this and noted that children are also likely to eat less food and drink less water per day than adults, so they would have lower ingestion rates, and this would act to lower the calculated hazard quotients. You will also need to change the averaging time and exposure duration of the calculation because people are children for only a limited proportion of their total lifespan. And you may also want to change the exposure frequency depending on differences in the lifestyle habits of children in a population compared to adults. For example, children may eat rice and fish more or less frequently than adults. So finally, question 3 is a rather broad question, but wants you to think about the assumptions and sources of uncertainty in these assessment of toxicity risks. And really here I want you to recognize that all of the 6 variables in this ADI equation are likely to be quite variable. So for example, concentrations of metals in water and food within a particular area can vary by considerably by orders of magnitude. And ideally, to assess this number that we use in this equation, we would want to have a large number of measurements of these metal concentrations and a large numbers of samples of a given water and food over a long time period. And this would allow us to properly characterize the average value of these metals in these various foods and water sources and the degree to which they vary. Likewise, body weight, ingestion rate, and exposure frequency are all likely to vary considerably between individuals within the population being considered. And all of these variables, so concentrations of metals in food and water, as well as body weight, ingestion rate, and exposure frequency, may also change considerably over the averaging time and exposure duration timescale that we've set to 70 years. That's a long time period. And so we need to carefully consider these potential sources of uncertainty when we interpret the hazard quotients. And one way of doing this is that we can try to assess the likely variance in each of these variables and propagate this variance through the calculation to give a sense of the range of hazard quotients likely for given these sources of uncertainty.